Hello, my name is Alexander Sergenko, and
I have to confess,
I'm a huge fan of Apache Flink. And that's why today we will look at Flink ML version 2, a new generation of the Flink ecosystem's machine learning library. But before we begin, please like this video and subscribe to my channel. Let's get started. The Flink community announced the release of Flink ML 2.0 in early January. Flink ML is a library that provides APIs and infrastructure for building stream-batch unified machine learning algorithms that can be easy to use and performant with near real-time latencies. 5 algorithm implementations were added in this release, which is the start of a long-term initiative to provide a large number of off-the-shelf algorithms in Flink ML with state-of-the-art performance. The following algorithms were added in the release: one-hot encoder for feature engineering, k-nearest neighbors, logistic regression and naive Bayes for classification, and k-means for clustering. During our journey, we will take a closer look at the k-nearest neighbors implementation in Flink ML 2. I also encourage you to prepare your IDEs, since today we will get our hands dirty. Let's look at today's example. The iris species classification is a kind of hello world in machine learning. The iris dataset was used in Fisher's classic 1936 paper, The Use of Multiple Measurements in Taxonomic Problems, and can also be found on the UCI Machine Learning repository. It includes 3 iris species with 50 samples each, as well as some properties about each flower. One flower species is linearly separable from the other 2, but the other 2 are not linearly separable from each other. The iris dataset can be used as a training and validation data for almost any classification algorithm. And today we will create a new Flink ML project using Java API, split the iris dataset into training and validation ones, read these datasets into streaming tables using Flink file system connector, and finally create a k-nearest neighbors model using Flink ML and train it using the training part of the dataset. And then we will pass the validation dataset to the trained model and check if it makes accurate predictions. Let's take a closer look at the algorithm. K-nearest neighbors is a simple yet important classification algorithm in machine learning. It belongs to the supervised learning area and is widely used in pattern recognition and data mining. It is also applicable to regression scenarios. The KNN algorithm predicts by calculating the degree of similarity between the input sample and each training instance. This algorithm is non-parametric, since it doesn't make strong assumptions about the form of the mapping function. In other words, because no assumptions are made, the algorithm is free to learn any functional form from the training data. The output of the KNN algorithm is a class membership. A class is assigned to an object that is most common among the k-nearest neighbors, where k is the number of neighbors. K is always a positive integer naturally. So prepare your IDE and
Let's get started.
it's time to look at our application. And since I use Maven here, we have to take a look at the pom.xml file. And there are plenty of dependencies. Most of them are related to the Flink ML lib itself, and others are related to the Flink core libraries. But let's start from the beginning. Well, the first dependency is Flink ML core. I use the version 2.0. The second dependency is Flink ML iteration, and it provides the iterative streams for some of the models that utilized in the Flink ML lib, the same version here. The next one is Flink ML lib itself. Flink clients will also use this dependency, and it is a Flink core dependency, and we use the version 1.14 here. The next one is Flink table planner. Since we will extensively use the Flink both table API and Flink SQL APIs, and the same version here. And the last dependency is Flink CSV. We use it because our training and validation datasets are in CSV, and the same version is here. So let's take a closer look at our training and validation datasets. But before we begin, let's look at the full training dataset. The full Iris dataset is available in the internet, and you can download it from Kaggle, for example, kaggle.com. This dataset contains 140 rows. Well, each column in the dataset is related to a specific characteristic of the iris flower. And the first one is sepal length. The second one is probably for sepal width. The third is for petal length. The fourth is for petal width. And the last one is a species. The species means the group of the iris flower. There are 3 groups are available, and I have a small note here. The third group stands for the Virginica species. The second species stands for versicolor, and the third one stands for setosa. Since model accepts only doubles, I decode the initial dataset and replace the 5th column, I mean species, with a double value. That's it. So at the next step, I've splitted the initial dataset that I believe I got it from Kaggle. I have split the dataset into 2 smaller ones. The first one is a training dataset, and it consists of 125 elements, and we will use the dataset in our training purposes. We will train our model using this dataset. And the second part of the initial dataset is validation dataset, and it consists of 15 elements. We will use this dataset as a kind of an indicator. We will compare the predictions that will be made by our KNN model with the predictions that are already set in the validation dataset. So we will pass these first 4 columns to our trained model, and we will compare the given prediction with the 5th column from the validation dataset. Simple, that's it. So let's get our hands dirty, and the first thing to look at is our main class. It's not a surprise that Flink jobs are usually right inside a plain Java application. It's an ordinary public class. I call it app. And we have a regular public static void main. And inside the main method, we will implement all our logic. And the first thing we will need is stream execution environment. the basis of our further development, and we also create the stream table environment using the stream execution environment created one step before. Well, now we have to read our iris dataset train, and we will read it using Flink file system connector. We provide a format. Obviously, it is CSV, and we have to define the name of the table to which this dataset will be read. And I call it iris CSV train. And now let's define the values, or columns, which will be read from the CSV. The first one is sepal length, the second one is sepal width, and so forth. The last column is species, and as I said before, it is also have a double type, and that seems pretty great. The next table that should be read is iris CSV validation, and this table will contain the data obtained from the iris dataset validation.csv. We use the same Flink file system connector and the same format here, and the result dataset will be read to the iris CSV validation Flink table. Looks pretty simple, but since our model, and I have said it a few minutes ago, accepts only doubles, but not simple plain doubles, it accepts a dense feature vector made upon a set of double values, and in our case, these values is sepal length, sepal width, and so forth. So we need a custom Flink SQL function that will transform our doubles, or in other words, our features, into a dense vector. And that's why we have to create a new scalar function. I called it the dense vector map function, and as you can see, it extends the scalar function. And basically in Apache Flink, when we creating a new scalar function or SQL function, we have to implement an eval method, and in our case, the method returns an object of the dense vector type, and in our specific case, it receives 4 values of double. But since dense vector is a kinda specific type, and the Flink type inference system doesn't have any idea about this type, we have to provide a so-called data type hint. And this hint will advise Flink and will say to Flink which format should be used in this specific SQL function. And in our case, we bridge the method to dense vector class. It looks pretty simple. No any surprise if I say that we have to register this function as a new Flink SQL function, and at this line I creating a temporary system function. I called it dense, and I pass the new dense vector map function as a second parameter. Now we are ready to use this scalar function in our Flink SQL clause. The first table stores the train features. It will store our train features that were obtained from the training CSV dataset, and that's why we running a new SQL query using our Flink table environment. And we are selecting the dense function applied to our feature parameters, and we read it as features column, and then we read species. If you remember, it is a 5th column in our initial data set as label from iris CSV train Flink SQL table that we have created, I guess somewhere here. Now we have a train features table that we need to train our KNN model. And the next step is to do the same thing, almost the same thing with our validation dataset. And we create a new table. I call it validation features. And we are selecting the same dance function, apply it to our features as features. But in that case, we are not reading the species column, since this dataset is a validation one, and we don't need the concrete class or concrete group in this table. The group or a species will be predicted by our model a few steps further. And then we simply execute the both tables and print their contents to the console. Let's look at the console. I will run the example and it probably will take some time to complete. Well, as you see from the console output, a few tables have been printed. And the first one is definitely our train data table because it consists of two columns. The first one is features and the second one is label. The features column consists of our dense vectors made based on the features given in initial training CSV. And the label is nothing more than a fifth species column from the initial datasets. And as we can see, there are 125 rows in this table. So it is definitely an iris train dataset. Well, let's go further. And there is a features column, and I guess that this is our validation dataset has been printed. It consists of only one column, and each row in that column is a dense vector made from our iris validation dataset, and it should contain only 15 rows. Great. We have a few steps to go, and the next step is to create the KNN, I mean K nearest neighbors model itself. And at the line 57, we are creating the model. The KNN object now stores our model. At the next step, we have to fit, or in other words, train our model using the training dataset that we have created a few minutes ago. And we invoke the fit method from the KNN object and passing the train features table into the method. Great. Since line 58, we have a trained KNN model and we are able to use it for the further predictions. So let's go. We have created a new output table. The output table will store the results of predictions, and we actually use the same object, the KNN model. We invoke the transform method and pass the validation features to the method. The result is obviously will be a list, and that's why we get the first element from the list, which is at the index position 0. Execute this table and print predictions to the console. Well, since I have already run the example, I have all predictions in place. These are our predictions, the final prediction table, and it consists of 15 rows, the same as our iris validation dataset. So let's check if our results are accurate. And I will choose some random rows from the predictions and compare them with the species that are given in a validation dataset. Well, the random row starts with 6.9. Let's look for the row in the initial dataset. Seems pretty similar. 6.9, yeah, that's it. And in the initial dataset, it has a species of 3. And the species of 3 is Virginica. Well, and the same class is predicted by our model, the third. It is a Virginica. Great. The next one. This one looks pretty nice for me. Let's check our validation dataset. Our row starts from 5.4, and that's it. Well, the species in the initial dataset is 2, and 2 stands for versicolor, and as you see, the same species was predicted by our KNN model. And so far, our model looks pretty good, since it gives an accurate predictions and accurate results. And let's check out the third row, and I guess it would be this one. Let's check our validation data set, and I'm looking for the rows that starts with 7.7, the first one. Great. Yep, that's it. And in the initial data set, this flower, each row is a flower, and this flower is of group number 3, and the group number 3 is again Virginica. And as we see in our predicted table, the same group is our prediction data set. Great. Seems that our model was trained pretty accurate, and it is able to give accurate predictions. As you see, the Flink ML2 KNN model produced quite accurate results during the validation stage. And it's worth noting that the KNN in Flink ML supports multinomial labels, whereas the logistic regression currently only supports binomial. In machine learning, the Apache Flink scaling strategy, operator and data parallelism, and consistent state management provide unlimited perspectives in ML engineering. If you are interested in machine learning, consider Flink ML 2. I hope you found this video informative and entertaining. Don't forget to like and subscribe to the channel. Bye. Have a wonderful day.